Okay, let's go ahead and proceed to our first problem. Give me 1 second. So for our first problem, this problem initially might actually look like a dynamic programming problem, due to the fact that we're asked to count something, mod 10 to the 9 plus 7. And one possible like DP you could try would be something like you go from left to right, and then you basically just count up how many M's and O's you get. And then each time you have some number of O's, you can then choose to match it with M's, right? Now, the problem with this, if we go left to right, is basically if we try to keep track of some information like how many M's there are, how many O's there are that we haven't matched. So let's just say K is equal to 2. And we go from left to right and we find M, O, O, another O, and then a M, and one more O. So a tricky part here is, let's say once you got to here, so far you have like 2 unmatched M's and 2 unmatched O's. And if you try to match your like O's to M's, you somehow need to keep track of the fact that this O can go to either one, but these 3 O's can only go to this M. So like it's not valid to try to construct 2 MOOs, right, in this case. Okay. Yeah, so to get around this, the big observation is let's just go ahead and process the string in reverse order. Cool. So if we were to process a string in reverse order, now it's suddenly a lot more clear. So we can see that at this point, we find 1 O, and then when we see this M, it's actually clear that this M is not satisfiable because we don't have enough O's to the right of it to form an MOO. And that's the main idea. And now let's think about a non-impossible case. So let's say we have something like this. Okay, so of course, for this case, the only valid solution is you take MOO and you take this MOO. And one way we can get to this is if we go from right to left again, we find 2 O's, and then we find this M, and we know that this M can only be paired with O's to its right. So there's only one way to do this, right? You have to pair it with these 2 O's. And a similar argument can be made for these 2 O's and this M. You have to pair it with these 2 O's. All right, let's do a slightly trickier case. Let's swap the M and O around here. Okay, so if we swap this M and O, then now let's consider how many choices we have, right? So first we, again, see 3 O's, and then we get to this M. And now we need to decide, right? So we know that this M has to be paired with 2 of the O's. And in fact, it has to be paired with 2 of them. So we can basically do 3 choose 2. Yeah, to figure out that, okay, out of these like 3 O's, we have to pick 2 of them to give to this M. And then once we've done this, there's going to be 1 O remaining. And then for this, and then next time we see another O, before we see another M. And therefore, for this M, we only have 1 choice because there's 2 O's to the right side that's not been paired. And we have to pick exactly 2 of them. Right, so we get 2 choose 2. And here we get 3 choose 2. Cool. And once we've computed this, we just go ahead and multiply them together, and that's the answer. So far we've been talking about this for L equals 1, where the string is not repeated, right? So just to summarize, we go from right to left, and we just track how many O's we've seen. And then anytime we see a M, we know we have to assign exactly K of those O's to this current M. So however many O's there are to the right of us, we choose K of them to assign to the current M, and then we keep going. And since we assign k of those O's to the current m, we can just decrease the number of O's we have to the right of us that are unassigned by k every single time. All right, so that's the solution for L equals 1. Now, it turns out to deal with a larger value of L is actually not that tricky. And the reason for that is because if you consider a singular like L, you can actually just, for a single repeat of this string, you can actually treat it completely separately from all the other repeats. And well, here's why. So for the last repeat, it's pretty clear that it's just the exact same thing as what we currently have, right? For the very, very last repeat. Now, for any repeated part of the string before that, all we need to do is think about what happens once we've done the last repeat. So once we've completely finished this repeat, then we're just going to go again with the exact same 3 O's followed by an M, right? Followed by another O, followed by another M. And this calculation is going to be the exact same because we've exhausted all the O's on this side. So essentially, all we need to do to take care of the large L case is we just take the answer for L equals 1, and then we take it to the power of L, and that's it. And then L is pretty large here, so we can't just sit here and multiply, but luckily we can do fast power. So essentially, a to the power of b is the same thing as, and this depends on if a is even or odd. Second. All right, so it depends on if it's even or odd. So if it's even, then it's just a to the power of b over 2 squared. Right. So for example, if you have like 2 to the power of 10, that's like the same as 4 to the power of 5 times 4 to the power of 5. So we just compute one of them. And then if this is not even, then you can go ahead and just have it be a to the power of b is equal to a to the power of b minus 1 times 1. Or sorry, times a. Yeah, so now we can do all these multiplications in a log number of steps. And that gives us our final runtime of, let me just type this out. Our final runtime here ends up being O of n to compute the L equals 1 case. And then we need to then take it with mod pal. So plus log of. Cool, and that's it for problem 1. Are there any questions before we move on? Right.